And I'm live. That is pretty cool. I don't know if the stream is going to work fine because I changed some things, but I hope it goes fine. So, yep, that is cool. Today is 6th of March 2026. And yep, let's just go. By the way, yep, today is also Friday. Stop the stream here. And yep, in like one of the last theory competitive programming streams, I did directed graphs. So let's today do the next thing from competitive programmers handbook cphp cphb. And yeah, so connectivity, strong connectivity. I don't know what this means, but we will figure out what this means. Strong connectivity. And if we get time, we will also see what the next chapter is. The next chapter says tree queries, and I think I have read this one before. Finding a No, I don't think so. I have read this one before. Yep, yep. I was reading up on queries. Yeah, cool. Okay. So strong connectivity. For now, let's go. And what is a strong connectivity? In a directed graph, the edges can be traversed in one direction only. That is the definition of a directed graph. So even if the graph is connected, this does not guarantee that there would be a path from a node to another node. Makes sense. For this reason, it is meaningful to define a new concept that requires more than connectivity. Okay, we need a new concept to define connectivity that defines more than just connectivity for directed graphs. A graph is strongly connected if there is a path from any node to all the other nodes. But wouldn't this create cycles? This might create cycles. This I think this will by definition create cycles. And yep, stream is going fine, it seems like. I think this will create by definition cycles. Why? Excally draw. And yep, shit, that is a bit messed up. Now it is not better, but now it is much better. Cool. So I think by definition, this thing will create cycles. That is, if we have a directional graph where there is a path from one node to every other node. Yep, look at this, because here also there is a cycle. And if we look at this from an abstracted point of view, let's say we have at least two nodes, and we like don't care, there might be other nodes also there, right? But the thing is, there is one path which goes through some nodes and leads to this B node, and there is this A node. And connectivity means that there is a path from A to B, and then also from B to A, which also goes through some nodes. And since this graph is directed, we cannot go, let's say this is path 1, this is path 2. Since this graph is directed, path 1 has to be different from path 2, because we cannot go back on a path because it is directed. So there is one path, this path 1. By taking this path 1, we go to B, and then taking this path 2, we go to A, back to A, and then we go back to B, and then we go back to A. And this is just like a definition for a cycle. So yeah, and there will be cycles in this strong connectivity. And if you want link to this book, which is pretty cool book, Yusako Guide. Is this the chat or this the chat? Shit, both the chats are same. Cool. Okay, yep. A graph is strongly connected if there is a path from any node to all the other nodes in the graph. Okay, that is just connectivity. Okay, for example, in the following picture, the left graph is strongly connected while the right is not. This is not connected because we can go from 1 to 3, there is a path. From 1 to 2, there is a direct path. From 1 to 4, there is a path, but there is no path from 2 to 1. So this is not connected, but this is strongly connected. This one is not strongly connected. Okay, and there is also complete graph, but complete graph, I think, is the term we use for non-directed graphs. Are only graphs. Complete graphs, I mean, not all of them, but no, both undirected and directed graphs can also be complete. Okay, what would be a directed complete graph? Directed acyclic graph, DAG, DAG. A directed complete graph would look like this. But I think the definition of completeness changes in this context. If the graph is directed, a complete directed graph or complete graph, complete digraph, okay, is a simple directed graph where every pair of distinct vertices u, v is connected by a symmetric pair of directed edges. Okay, by a symmetric pair. So if we, for every node which is connected, they are connected in both ways, and that is just directed complete graph, complete digraph. Okay. Now, the right graph is not strongly connected because, for example, there is no path from 2 to 1. Cool. The strongly connected components of a graph divide the graph into strongly connected parts that are as large as possible. What does that mean? The strongly connected components of a graph divide the graph into strongly connected parts that are as large as possible. The strongly connected components form an acyclic component graph that represents the deep structure of the original graph. For example, this thing. Okay, there are components which are strongly connected. The strongly connected components of a graph divide the graph into strongly connected parts that are as large as they can be. Strongly connected parts that are as large as they can be. This component, which is just a subgroup of nodes and edges, this is complete or strongly connected. This is also strongly connected, this is also strongly connected, and these strongly connected components of a graph divide the graph into strongly connected parts that are as large as possible. What do they mean by strongly connected parts? Like, uh, are they calling each component a part? Something like that. The strongly connected components form an acyclic component graph that represents the deep structure of the original. Now, for example, the strongly connected components are as follows. The strongly connected graph is as follows. Okay, shit. If we replace these components with single nodes, then this is what we have, and this corresponding component graph. Okay, these strongly connected components give rise to a divide the graph into a strongly connected parts that are as large as possible. But these parts are not, this resultant graph is not a strongly connected graph. These are not a strongly connected graph. Form an acyclic component graph. They are calling this thing acyclic component graph because it is made up of components which are strongly connected. The components are A is of two nodes, 1 and 2, B is three nodes, 3, 6, 7, and C is 1, and D is also one node. A component graph is an acyclic directed graph. Acyclic directed graph, so it is easier to process than the original graph. So it is easier to process than the original graph. Since the graph does not contain cycles, we can always construct a topological. Yes, we can construct a topological sort if there is. Hello, Eric. And somehow the chat is on two sides. I don't know how that works, but yeah. And yeah, this is cool. Connectivity. We can always construct a topological sort and use dynamic programming techniques like those presented in chapter 16, which was how to construct a topological search. Topological, if there is no cycle in our directed graph, then we can always construct a topological sort, and we always have to go to a node's parent until we find a node which does not have a parent. That would be our like a starting node, and from there we can just do BFS and we will be okay. Hmm. Okay, so what have we seen till now here? Just like writing it down. Strong connectivity, and yep, can you like tell me if the audio is cool or not? I changed some things in OBS. I don't know if the audio. Shit, my face is too big. Oh yeah, shit, my face was actually too big. Oh, much better. Actually, much better. Yep, thank you. That is cool. Strong connectivity. Hmm. Directed graphs, which and yep, strongly connected graphs are always cyclic and cyclic. Cyclic. Mhm. And we can divide them into uh, strongly connected components. If a graph is not completely strongly connected, then we can divide it into strongly connected components, which give us a different graph. We call it component graph or whatever we want to call it, and that other graph is acyclic, that we can call it a meta graph, and where each node is representing a component which is strongly connected. Okay. Mhm. Divide the graph into strongly connected components. Okay. And strongly connected components and get a meta graph which is acyclic. And while I write it down, just like it looks cool. A with acyclic with a like C. Okay, and there are algorithms we can use to find this out. And share, I don't think I'm going to need this. Not at some point I might, but not right now. But it's still like since I started this stream, I'll have to do this. Hello, and it's a 777. Kusa Raju's. Shit, that looks like a Indian name. Like the second half of it, Raju is an Indian name. So algorithm is an efficient method for finding the strongly connected components of a directed graph. The algorithm performs two DFS searches. The first, okay, so now our task is to efficiently find strongly connected components of a graph. How can we find strongly connected components of a directed graph? And strongly connected components are components in which we can go to any other node. Yep. we can reach any other node. Mm, I think if there is a cycle, then all the things, all the nodes on that cycle are going to be strongly connected. So we just have to find out cycles. I think if there is a cycle, then all the things on that, all the nodes on that cyclic path are going to be strongly connected, because by definition, since we are calling this thing a cycle, then from this node I can go to all of these nodes. How? Just like walk along the path, and from this node I can reach all the other nodes, and like, yeah, continuously I can say the same thing for each and every node. So all the nodes on a cycle are strongly connected. We can call that thing a strongly connected components. So given a random graph, our goal would be to figure out all the cycles. Let's say for this graph, how do we figure out a cycle? We begin from some random node, let's say, and yeah, we begin from some random node. We go along this edge, and along this edge we reach 4 and we reach 2, right? And then from 2 we go back to 1. We saw that 1 and 2, but we also have to keep track of the whole path that we are taking. Yep, we also have to keep track of the whole path. Raju Elgo is real. Shit, I believe you. Okay, we have to keep track of the whole path. Okay, what are the things that we need to keep track of in this DFS or BFS? Do we want to go layer by layer? We don't necessarily have to go layer by layer. No, we will use BFS. Instead, we will use DFS. And what are the things that we need to keep track of? Things to remember. One is the path. Why the path? Because we need to know all the nodes which are along the cycle. And if we do have the path, and one more thing, let's say we began for a single path. Let's say for now, for a single path, let's say we began from a random node like this. When the cycle ends, if we are on a cycle, this the node which is repeated might be the one from where we started, or it might be some other node. And in the first case, the cycle would be this whole path from the start, and in the second case, the cycle would be this much of the path. Hmm. So we need to keep track of these things. And shit, let's say this is also connected to some other node, some other path, and the like looping back happens only for when we go from this node to this specific node, and not on this node. So we, yeah, which just means we have to keep track of path, which means for this I have to know the parent, for which I have to know this parent. Okay, so there are a couple of things. One is finding cycle, and then let's say if we have a method of finding out cycles, do we take that cycle and put it away? What kind of cycles can there be? Let's say this is our chain of nodes which are connected, and there is a cycle like this. Or more correctly, let's say there is a cycle like this. So we can, in this case, we can take all of this as one component, and all the other nodes which might be those nodes singularly would form one component each. But there could be more complicated cycles. Let's say one cycle is like this. Shit, that is messed up. We are shit in this. Would the direction of the cycle matter? The direction of the cycle would also matter. The direction of the cycle would also matter. And we are not trying to come up with the algorithm. We are trying to come up with the algorithm, but we do not have to invent it. We can just at least think about it, analyze what we have at our hands, and when we actually go through the Raju algorithm, we will have a better perspective reading it. So that would be cool. Yep, shade. The direction also matters. The direction also matters. Let's say we have multiple nodes like this. Cool. These are connected like this in this direction. And then we have two other nodes like this. And shit, this should not be the direction. This should be the direction. Like this. Here. So in this case, the direction of the cycle is like this. And I think we cannot, yeah, it matters. The direction matters. If we have this cycle with a direction like this and another cycle, let's say, with a direction like this, a direction like this, and we go here and we go here, then we can, from let's say this node, we can obviously go to any other node in this region, but we can here make a decision and go here and go to all the other nodes here. So we will consider always the bigger cycle. And now, shit, we also have to consider this smaller cycle. This is a like big cycle, like this. Hmm. Okay, let's read the actual algorithm. Kusaraju. That, that is a not an old person. Shit, he seems like new, and he actually does seem like an Indian person. Here by Rao Kusaraju. Shit, he actually is an Indian from IIT. IIT Kharagpur. Shit, that is something. That is something. He actually is an Indian. Okay. Uh, Here what do we have? Okay. Kusaraju's algorithm is an efficient method for finding the strongly connected components of a directed graph. The algorithm performs two DFS searches. The first search constructs a list of nodes according to the structure of the graph, and the second search forms the strongly connected components. Okay, search one. The first phase of Kusaraju's algorithm constructs a list of nodes. Wait, according to SR, Kusaraju invented this algorithm. SR Kusaraju invented this algorithm in 1978. That is recent, I think, but did not publish it. In 1981, the same algorithm was rediscovered and published by M. Sharir. Sharir. The first phase of Kusaraju's algorithm constructs a list of nodes in the order in which a depth first search processes them. The algorithm goes through the nodes and begins a DFS at each unprocessed node. Each node will be added to the list after it has been processed. In the example graph, the nodes are processed in the following order. Wait. The first phase of Kusadaju's algorithm constructs a list of nodes in the order in which a DFS search processes them. Okay, that makes sense. Kind of sort of pseudo topological sort, because we are going from the parent to however far we can. That is why depth first search. The algorithm goes through the nodes and begins a DFS search at each unprocessed node. Each node will be added to the list after it has been processed. Okay. And wait, I was getting a random call. That is crazy. Okay. In this example, the graph. Wait, wait, I will. I think I will have to see how it is. Wait a minute. And I'm back. Yep, cool. Shit. I got a call, but okay, cool. Back to this. Cause wait, my camera also. It camera is working. Cool. So in this algorithm, Kusaraju algorithm, we use this for finding strongly connected components in a directed graph. That is the goal. And this thing does two DFS. Search one, what does it do? In search one, it just picks a random node and starts its DFS process and keep it has a list, and whenever it sees a node which has not been processed, it processes the node and adds it to the list. So in this example, the nodes are processed in the following order. What is this order? The notation, this means the processing means that processing the node started at time x and finished at time y. Okay, thus the corresponding list is as follows. So let's, okay, yep, like this one, this node number one is the first node which was processed because it processed at time one, and from one we went to two. So we added one to our list, and then we added two to our list. Then the third thing was node number five. Then it was node number four. From node number four, we didn't go anywhere else. Then node number four, five, six. What was the next node? From we went back to five. We considered five as finished. Then we went to node number two. We considered that finished because we cannot go anywhere else. We can only go like to this node here, and we did go to this node. So we considered two finished, then we considered one finished, then we started processing node number three. We went to two, which was already finished, so cool. Then from three, we went to seven. Okay, we only go to nodes which have not been processed. So after two, we didn't go back to one. From three, we didn't go to two, we went to seven directly because two was already finished, or yeah, considered finished. Then from seven, we went to six. Okay, so the order should be 1, 2, 5, 4, 3, 7, 6, or the complete opposite. Shit. Okay, we add them to the list. The algorithm goes through the nodes and begins a DFS at each unprocessed node. Each node will be added to the list after it has been processed. Okay, after it has been processed. So the node which was processed first was 6, then node number 4, then 5, then 2, then 1, 4, 5, 2, 1, 6, 7, 3. 4, 5, 2, 1, 6, 7, 3. Okay, cool. Processing time. This is what we do in search number one. Okay, how can we do this in like implementation terms? I think we can do this. We can have a bitmap Yes, we can have a bit set in C++. If we are talking in C++, we can have a Boolean vector which will be off if the node is not processed, and yeah, we will recursively keep calling the function, and after the node is processed we will put it into the list. Cool, cool, we can do this implementation terms. And in the second search, what do we do? The second phase of the algorithm forms the strongly connected components of the graph. First, the algorithm reverses every single edge in the graph. Reverse every single edge in the graph. This guarantees that during the second search, we will always find a strongly connected components that do not have extra nodes. After reversing the edges, the example graph is as follows. What does this guarantee, reversing the nodes? This guarantees that during the second search, we will always find a strongly connected components that do not have extra nodes. Strongly connected components that do not have extra nodes. Okay, I guess it will make sense with more context. After reversing the edges, the example graph is as follows. Okay, we reversed the edges from this to this. Cool. After this, the algorithm goes through the list of nodes created by the search in reverse order. So where the last was 3. Okay, in reverse order. If a node does not belong to a component, the algorithm creates a new component and it starts a DFS, depth first search, that adds all nodes found during the search to the new component. Okay, in the example, the first component begins at 3. Okay, we consider that a component begins at 3. Note that since all edges are reversed, the component does not leak to other parts in the graph. That this thing like still does not make sense. Why does it not leak to other parts of the graph? That point still does not make sense. And I think now the face is like a bit too small. No, I guess that is big enough. Note that, okay, shit, this does not make sense, does it? Shit, I think it does make sense. Reversing the edges. If we reverse the edge, let's say we had a cycle like this, and we are only considering these things. Okay, let's say we have a cycle like this, right? In some particular direction, we move in this cycle like this, right? And then we have fringes like this. But if we reverse the direction of the nodes, then what we have is these directions are reversed. So we have this and this, and now since from this cycle we cannot go outside to these fringes, we can just ignore them because we cannot go outside, we can only go in here, in these fringes. So cool, shit, that is cool. Reversing the edges to, but that would also mean if we had, let's say, before we had something that was pointing into this, it will be pointing out and we would still have fringes. But I think we are fixing that with the order. These nodes, the list that we made because of the first search, that list will have these internal nodes first and then these nodes later on, because we probably came into this graph from those nodes, into this circle from those nodes. thing. Okay, let's first understand the algorithm, what it is saying. Reverse order. Okay, if a node does not belong to a component, the algorithm creates a new component and it starts a DFS, depth first search, that adds all new nodes found during the search to the new component. In the example graph, the first component begins at node 3. In the example graph, the component begins at node 3. Note that since all edges are reversed, the component does not leak to other parts of the graph. That sentence still does not make sense because it could leak potentially still. The next, let's see, the next nodes in the list are 7 and 6, but they already belong to a component. So the next new component, okay, how, okay, so we began a DFS at 3. We went to 6, we went to 7, we went to 3, and we considered that a component. Okay, the first component begins at 3. The next nodes in the list, how did we end up saying that this thing is going to be a component? And then we just, should 2 SAT is the satisfiability problem, which is like NP complete or something. Should this okay, 2, if this is the satisfiability problem, SAT. The time complexity of this algorithm is O of n plus m because the algorithm performs 2 DFS. The 2 does not matter. But shit, this thing still does not make sense. And yes, login. Wait, this might show some incriminating evidence. Okay, shit, I lost my account. Unfortunately, shit. I will log in later on. But okay, shit, this thing does not make sense. How did we end up concluding that 3, 6, and 7 is a component? We started from 3. We, after this algorithm goes through the list of nodes created by the search in reverse order. The second phase of the algorithm forms the strongly connected components of the graph. First, the algorithm reverses each edge in the graph. This guarantees that during the second search, you will always find strongly connected components that do not have extra nodes. After reversing the edges, the graph looks like this. Okay, after reversing the edges, the algorithm goes through the list of nodes created by the first search in reverse order. If a node does not belong to a component, the algorithm creates a new component and starts a DFS. Okay, so at 3, we, because 3 is the like thing here at the last, we are going in reverse order. So okay, we begin with 3, and 3 is not a part of a component. So the algorithm creates a new component and starts a DFS that adds all new nodes found during the search to the component. Okay, so 3, 6, 7, then we saw 7 and 6, which were already a part of a component, so we didn't do anything. We saw 1, from 1 we went to 2, back to 1, which was visited, so again, yep, then we 5 and 4. Cool. Shit. And this is guaranteed to work. Okay, and this thing does make sense. Let's implement this. That would be cool. Let's actually implement this. And shit, I should have, shit. Okay, that is 560, I think. Okay, cool. um Kusaraju algorithm. CPP and shit. Fine. write a function called which will what will it return? It finds these components, so it will return a list of numbers, a list, a 2D matrix, a yeah, two-dimensional list, a list which has lists of numbers. Shit, I will have to configure my stuff in here. Vector of integers will be written to Saraju. And what does this take in? This takes in two-dimensional vector. Adjacency matrix, let's call it. And okay, so let's do search number one. In search number one, we go through parent I equals 1, I smaller than equal to edj dot smaller than adj dot size I plus plus. And okay, we need a visited node. Yeah, we need a visited thing. Yep, we need a vector of boolean visited whose size would be adj dot size. Everything would be false at the start. Vector does make sense. This should have, okay, shit, I think I'm using the wrong LSP because this should have made sense without this bool, because we are giving here false, and this thing should be using a feature from C++ 17 called automatic temp shit class template argument detection, I think. Argument detection. Yes. CTAD feature from C++17 where we do not give the type inside template. It is inferred from what we give in here to the constructor. Let's see what the LSP is saying. How do we see the LSP version? Shit, we see the LSP version from there is a specific file we have to change. Hello, long time no see. Happy Holi, by the way. Give me a lang d YAML file that specifies std and that specifies C++ version 23 for C++ files and for nothing for C files. Can we do that? And the file is inside library preferences. Shit, there should be a file here named langd. We will make one. Config.yaml, I think. And there is also a problem with neovim plugin treesitter.lua line number 6. This, if this, then this, and we can just paste this here, and this should work probably. also the error with new vim. This error inside plugins. Presetter.lua line number 6 is this thing, require this, and dot setup is does not work. New vim treesetter.config. Shit, dot configs. I don't think dot configs is a thing. I think now we are okay. Now we are okay. Okay, cool. Yup. CD competitive programming and in Kusana Cruz algorithm. And yep, cool. There's no problem with this now. And C++ 20 features, we should also be able to use this thing. This is a C++ 20 feature. And also ranges. Yes, ranges are a thing. And we should also be able to say void function auto reference x. Yep, that's good. Now for int I smaller, yes, we will keep going. Okay, and we also need a vector. Let's say order adj dot size. No, we don't need a size. This is going to be a vector of integers. A vector of integers, and when we process some vector, then we add it to the list, for which we need a DFS algorithm. DFS, first DFS, this will take in int I, the current node that we are at, and visited vector, which is just a vector of boolean. And does it need to have the list? Yes, it does need to have the list to add stuff called order. Okay, cool. Only called if I not visited. Yep, this will, so we will suppose that I is not visited. So first we will process I, which means for int x. Shit, we also need the like adjacency list, which is something that is required here, like of course adjacency list here adj of I, that is every node x that we can go to from I, if not visited x. If x is not visited, then we will say that x is visited, right? X is visited, and call DFS on x, call DFS on x with x as the first thing, and then visited. Or I guess we can make these things available here. Bool visited and vector of integers order, and we don't have to send these things like this. Okay, and cool. This and adj, and then at the end when we have visited, like processed the ith node, we'll do order dot pushback I after processing, and visited and order. Visited dot assign size would be adj dot size, and everything would be false. And here, shit, order dot assign size would be, this does not need a size would be 0, and there is nothing at the start. And cool, for int I, and shit, we also need visited is there. Yes, everything is false. I equals 1, I smaller than 80. Let's call this thing n equals 83 dot size n smaller than equal to n I plus plus equal to n or smaller than n. Yeah, smaller than n. If not visited I, then visited I equals true, and dfs first call this thing with I, call this thing with I and adc. It is immediately. Okay, we should get our order after this. Invalid operation, that does not make sense. OS stream, okay, yes, shit, of course. Include IO stream. Cool. After this, see out order. Cool. And let's say for now this thing returns white. Int main. Cool. We need a vector of vectors of integers, or we can use class template argument detection and define our 83 like so. Stuff like this. Okay, what is this thing? From 1, hello, from 1 we can go to 2. Wait, the original one. Yep, this one. From 1 we can go to 4, and we can go to 2. This one is 0, so nothing, empty, number 0. And cool, wait. I think here if I this desktop, and cool, this is number 0 and number 1. From 1, shit, from 1 we can go to 2, and we can go to 4. Cool. And then vector from 2, from vector number 2 we can go to 1, and we can go to 5, and that is it. And then from 3 we can go to 2, and we can go to 7. Cool. And then from 4 we cannot go anywhere, so 0, we cannot go anywhere. How do we create an empty vector here? Just say 0, or vector of integers 0, or we here give 0 like this. And then from 5, we can go to 4 and nothing else. From 6 we can go to 5 and to 3. from node number 7 we can go to node number 6. That is it. And cool. Yep, that is kind of it. This desktop, cool. And if we pass this to Kusaraju algorithm, we should see the correct order. Compile and run, and error because we do not have this thing, command g++15 not found. Shit. It will be found in a minute. Okay. So this will be search number 1. Cool. Then search number 2. In search number 2, yeah, we will start to go in reverse order in this list of nodes that we should get after search 1. And shit, I think we just download GCC instead of G++, and that works. GCC should be there like automatically. Okay, I think the code for search 1 is correct. Then we just have to do search 2 and we will be done with this. Kusaraju, we will have a way of finding out components, which I think is very, very important. Like, of course, you would need to find components connected, strongly connected components inside a directed graph. And then it seems like there is the satisfiability problem. Downloading. Cool. Do I have G++15? No. Yes, I do have G++15. Cool. And it took 2 seconds and we have the correct shit. No, we do have the correct thing. 4521673. 4521673. Cool. That is like perfect. Cool. And now we can move on to loop number 2. Search 1. Right. Search 2. In this, we go through these things that we found for integer x in order, and we have another visited graph. And yep, so we need to first initialize stuff. Vector of integers, we will call this response. The thing that we are going to return here, vector in the shit vector, and at the end return res, and we need to reinitialize visited dot fill. This should work. Visited dot fill with it. There is some problem with this vector boolean. No thing named fill. Okay, I guess fill is another function. Yes, it is inside algorithms. Visited dot begin and visited dot end. Fill this where false. Cool. Nothing is visited. Fill this with false. Okay. If the current node is not a thing, bool inside equals false. That is if we are inside a component or not. If we are inside a component, then say if we are inside a component and if the current node, if visited x, if the current node is visited, then we have made a cycle and we can legit just break out. That would be cool. So we will just say inside equals false for the next iteration. Else, if not visited, then this dot back dot push back x. Okay, and else if we are not inside a node, if we are not inside a node, the current node cannot be visited by definition. So we will do res dot push back a new vector of integers, a new vector of integers which has one element, or this we can say this, and that element is x. Cool. And yeah, and shit, we can use some advanced features here. The LSP is like acting wonky. It is giving like it is not coloring things properly. All of this white stuff, it is not coloring stuff properly. But here we can say no, discard with a message, like why did all this if not for the return value. Now if we call this function without if we call this function without capturing the return value, then we will get some error, not error but a warning error with the message. So that is cool. So let's const response type specific for auto const, and then for auto reference x in res cout x. Excellent. This should be working. We should be able to print x. OS stream invalid operands to binary. OS stream basic char. We should be able to print this. The type of x is, okay, x is a variable which is a vector of integers, a reference to a vector of integers. We should be able to print this. Is it because of reference? Shit, it was because of reference. We cannot give a reference as a reference. Okay, that is crazy. We cannot give a reference as a reference to some other function. That is a bit messed up, I would say. But okay. Let's see, what do we have? Okay, we have 4 as a component, and shit, everything is a component in itself. That is messed up. Because at the end we do have to say visited x equals true. We also have to do inside equals false, no, inside equals true at some point, which is this point. Compile, and now everything is a single component. That is also messed up. Visited x equals true, inside equals true at this point. Okay, then we go to 6 and we see yes, we are inside. That is very cool. And okay, pretty cool. Shit, we have to do DFS, and no, yeah, shit, yes, fuck. Shit, yes, we have to do DFS. We have to do DFS and this thing. Yep, shit, yep, okay. So we'll call DFS on 3 till we roll back to 3, I think. Okay, so we need a second DFS thing, a function. Second DFS function takes in I, vector, and shit, we also have to reverse the whole thing. Reverse the graph. Shit, yes, shit. We have to reverse the whole graph, which is messed up. Okay, we will have a separate function which reverses the graph, returns reference, reverse takes in a vector of integer, reference atj. Okay, cool. Vector, or we don't have to say this, we can say response of size is going to be adj, same size as this, adj dot size, and every element is going to be a vector of integers. At the end is return this response which does not match the type that we want to. Okay, cannot bind to a temporary. Return a copy in that case. Okay, for int I equals 1, I is smaller than adj dot size I plus plus for every x that is connected to I. Since we need to reverse the direction right now, we have I to x. What we want is x to I. Okay, how do we get that? We get that by simply saying response x dot pushback I. Cool, and yeah, the thing is now reversed. Okay, so after the first search, let's get our autoconst reverse adj would be reverse give in the forward adj. Okay, okay. Second DFS, we will call second DFS with this reversed adj thing. Hello, increase volume. Shade is volume low. Hello, like do not call me sir. Just like Jatin is fine. Could you help me in a one-by-one mentorship session regarding career decision, not more than 15 minutes? I mean, yes, we can have a talk. If I can be of any help to you, that would be cool. I myself need mentorship in career decision. But yes, we can have a talk, and let me increase the volume. Yes, LG WebOS, somehow it is there, and output volume is cool. I can make it left or right. Now you must be hearing everything from your right. Hello from your right, and hello from your left, and now hello from the middle. Cool. Wait, I am his manager. You can transfer me. Yes, you can transfer him. He will handle everything. Yeah, yep. He will handle everything. He's the manager, the controller, or he's the modular. We call him. Hmm. Okay, second DFS. Second DFS. For the second DFS, when we call this DFS, shit, we do need the visited thing. We do need, yes, we will need the visited thing. Only call if I not visited. So we will assume that I is not visited. If I is not visited, then cool. Then yeah, if I is not visited, then it is cool. Shit, we need. Shit, we need to give this function the return value. So we need a vector of integers. We will call that thing connected components, or more likely strongly connected components. And when the second phase begins here, we'll say strongly connected components dot assign 0 0, yes, 0 integer. Wait, do we need assign? I think, yeah, okay, cool. Assign is cool. Okay, assign is cool. So in this, first of all, we will add to strongly connected components dot back dot pushback, and LSP is shit. Like actually LSP is shit right now somehow. Pushback I and go to, since we are going to call DFS on this, for every X that is connected to EDJ I, or more likely we should call this, substitute ADJ with reverse ADJ. Shit, it didn't change. ADJ with reverse ADJ globally. Okay, does not provide a call. Yes, shit, we have to do this. Good. Wait, don't call me that. Okay, you have said that before, but I will keep calling you that because yes, uh, yes, I have like power. I have the mic here. I can speak liberal. X for everything X that is connected. Okay, if not visited X, then visited X equals true, and DFS second with X and reverse ADJ. But if X is visited, then just like break. If X is visited, then don't do anything. Yep. If X is visited, then do not do anything. Cool. We do not break, we just do not do anything. Does it make sense? I think it does make sense. So cool. Cool. Here, if not, if visited, on X. If X has been visited, then don't do anything. If we are inside a component, no shit, that does not even matter. That does not even matter. Inside, no. If not visited X, if the current node that we are at, it is not visited, then that marks a start of a new component, which means we will do this dot push back a new vector of integers with 70 initially, and we will call dfs second with x reverse order adj shit no matching function call to dfs second REVERSE reverse ADJ REVERSE reverse ADJ const shit. Why would this ever be const? Okay, yes. And we should not be seeing error, but we are seeing error. That is messed up. Wait, what are you doing? I think I'm trying to find out. First, okay, we are implementing this algorithm called Kosaraju algorithm. And what is this algorithm? This algorithm finds inside a directed graph components which are strongly connected, and component is just a subset of a graph, right? Like if this is the whole graph, then a component would be 367, which is a subset of the graph. So we are finding components which are strongly connected, and strongly connected means inside that component you can reach every node from every other node. Cool enough. And this is what we are trying to find out using this algorithm called Kosaraju algorithm. And the, it should be working, at least the first part. There are like two searches in this algorithm. Search 1 is completely fine. We messed up a little bit with search 2. Let's see. Reverse ADJ, which part is giving error? There is no console.log here. Yes, there is no console.log here. Is this working till now? Till this point? It is working till that point. Okay, where do we get the error? Are we stepping outside our limits? Okay, shit. We gave error inside this function. Okay, not console.log. You said x. Compile and shit. Not even once. We got error in the first try because we should be going in the reverse order. Shit, yes, we have to go in the reverse order, like it said in this. We have to go in reverse order with like italic. So we have to go in the reverse order. So for an I equals order dot size minus 1 I greater than, do we have to go to 0? We do have to go to 0. Greater than equal to 0 I minus minus, let's say x equals order I. That's fine. Compile and we do C3, which is correct. Okay, till at which point do we get error? In the second DFS. Okay, parent I, that is reverse. Okay, yes, shit, that is reverse. This is not reverse. Not console.log. I, till which point are we moving? We are going from 4 to how did we get to 2 and 3? That shit. We shouldn't be able to go to 2 and 3. Are we reversing in the right order? Yes, shit, yes, we should check if this reverse ADJ is correct or not. Auto x reverse adj and see out, compile, and why do we see this reverse adj later on? That does not look good. Still we are seeing it later on, which means we messed up somewhere. Okay, because we are print. Yeah, shit, we are printing there. Not in reverse. We have to print here. Shit, I think. Okay, we have to say visited x equals 2. And are we okay now? We are not okay now. But this is the reverse thing that we have. 2. This was our original graph. And this is the reverse graph, this thing. So from 1 we can go to 2, that is cool. From let's say 7 we can go to 3. Do we see that? From 7 we can go to 3, and from 6 we can go to 7. From 6 we can go to 7. Cool. From 5 we can go to 2 and 6. From 0, 1, 2, 3, 4, 5 we can go to 2 and 6. Okay, the reverse graph is cool, no problem with that. Yep, no problem with the reverse graph. 3, which is being printed because of this thing. If not visited x, then put x equals visited. Pushback. Are we seeing error because of this? We are not seeing error because of that. DFS second. Okay, we are getting error inside this thing. We are not even seeing this one even once. Yes. Compile 3. Okay, we called this for 3 and reverse ADJ 3. Do we not see reverse ADJ 3? Let's again print for auto x in reverse ADJ see out x with line. This is 0, 1, 2, 3. From 3 we can go to 1 and 3. Shit, this is 1, 2, 3. From 3 we can go to 6. From 3 we can go to 6. I think reverse ADJ is a bit messed up. Size is this for I, every I, k, and push back I, which is correct. We should here see in this from 3 we can only go to 6. We should see 6 printed there. Hello, is that BFS approach or DFS? I'm guessing DFS. Yes, you are guessing right. It is DFS. DFS for finding out strongly connected components. Uh, Here, strongly connected components inside a graph. compile, and we see 3, which actually is messed up. We see 3 being printed, which is messed up, which means our reverse ADJ is a bit messed up. Reverse ADJ dot size is 8, which is correct. Which is correct. Which is correct. So what is the problem? Which is correct? For int I equals 0, I smaller than reverse ADJ dot size I plus plus, and let's say cout I, right? Cout I and a bit of space, and then reverse ADJ, everything that is connected to I, every place that we can go to from I. 0, we cannot go anywhere. Then 1, 2, 3. From 3 we can go to 6. So that should be working, but it is not. And also, why do we have this like empty? Okay, shit, we are getting this new line, by the way, because here in this case, in this if condition, we are adding a new line, but here we are not adding a new line. Yes, shit. So and then we here have to do new line, and we can avoid using end line here. Okay, cool. From 0 we cannot go anywhere because there is nothing to go to. From 3 we can go to 6, but we do not see that. Second DFS, cout I. And cout X. So from, okay, we like never go inside this thing, it seems like. Reverse ADJI, it seems like ADJI does not exist. We are never going inside this for loop, it seems. I. Okay, yes, we are not going inside this for loop. Why are we not going inside this for loop? Reverse ADJ dot size I. Okay, reverse ADJ I does not exist. Wait, is it because of this? Yeah. Hello. How many hello do we see? We see a single hello. Okay, shit. The error is because of this line. This line here is strongly connected components dot back dot push I, which should work because here if x is not visited, then we are doing rest dot push back. Shit. Okay. Okay. Shit. I think we have to say 0 here, and now we might be okay. We are not. Okay. Still shit. Wait, res makes sense. Makes sense. Shit. Strongly connected components dot pushback 0. Cool. It is working. Es funktioniert and return strongly connected components. Cool, and don't do this res thing. Delete this. Delete. Delete. Compile, and these are the components. Cool. Okay, shit. This is working now. 3, 6, and 7 make one component. 1 and 2 make one component. 5 is 1 and 4 is 1, which is exactly right. 3, 6, and 7 make one component. 1 and 2 is one component. 4 and 5, one component each. I don't know the full question, but I'm guessing we have to make a graph fully connected. We should be able to go every vertex. No, we do not have to make a graph fully connected. Make a graph fully connected, like we should be able to go to every vertex. Yep, we should be able to go to every vertex. We do not want to change the graph. The graph is fixed. We are just finding out which small or which subset of vertex we can take which are fully connected. Like in this graph, if we were to look at this graph a bit more closely, in this graph, this whole graph is not connected, but if we were to only take 3, 6, and 7, this subset of the whole graph, this is connected. And similarly 1 and 2, if we were to take just these two nodes out of all of the 1 to 7 nodes, these two nodes are fully connected, and for 4 it is not fully connected to anything, so just 4, and same for 5. So these we have here 4 components which are just subsets of the whole originally full graph, and these things are fully connected amongst themselves. 1 and 2 fully connected, 3, 6, 7 fully connected. So our goal is to find out all of these subsets of the original graph which are fully connected. That is it. And hello again. Hi. And shit, okay, it works. It works. That is a bit cool. 97 lines of code. Shit. Okay, let's see if maybe we can ask Claude to make this optimized a bit. I think it can optimize this. We will be able to see our mistakes. Authenticating, it is somehow taking time. There is also LM Arena, AI Arena. Okay, it is still thinking. Direct chat with Claude Opus 4.6. Okay, your conversation and personal information. Okay, make this code more optimized and shit. Okay, there are some things we can drop, like this function to print vectors. Don't need this. If we remove this, right, take this and optimize this a little bit. Yes, agree. Whatever it was. This is like still a bit long, but okay. What are the things that Claude has changed? Stack. Okay, it is using stack for something. Let's see. Okay, things are not defined outside function scope. They are passed in. ADJ, visited, and order. Iterative DFS to avoid stack overflow. We create a frame struct node index stack dot pushback I0. We create a vector of stacks where we have node and index and index. Okay, shit, we don't need this node index, by the way. And okay, okay. I think I understand what is happening here. Instead of calling first DFS internally from here, we are creating a virtual stack, iterative DFS. Okay, shit, I didn't know that we could do DFS iteratively. To avoid stack overflow, we can do DFS iteratively by synthesizing a stack, I think. Shit, that is cool. That is cool. That is cool. That is something more similar to BFS, the way that we have a queue in BFS. Yep. Can I somehow get the code? I think wait. GitHub.com gist. I think I can create a gist. How do we create a gist? New gist. Yep. Create secret gist. No one should know. While C++. Oh, wait. Kusaraju.cpp. Cool. Spaces. 8 indentation 8 spaces, yes, use spaces, wrap, no wrap, cool, read secret gist, and copy this. Now you have the code. Cool. Shit, but I never knew that. Shit, we can do DFS iteratively without recursively calling the function again and again. That is cool. And this is similar to BFS. In BFS, we yes, in BFS also we do not do any recursive call. We just have a queue which we keep filling and we keep going while the queue is not empty. And we are doing something similar here. Cool. And okay, yes, there is a difference between queue and stack. There is a difference between queue and stack. Yep. Okay, and DFS second in this also we are using the stack. And here the stack is just an integer. Here the stack was much more than a single integer. Okay, and then shit, that was one thing. Compute first order, get the order, then reverse ADJ. We are reversing it in place. Okay, cool. Then visit it, make everything false. SCCS. Okay, and then SCCS return. And here in place is cool, in place empty. Shit, that is much better. Shit, that is like actually much better than doing what we were doing here. Yep. Instead of this, we could be doing in place empty. In place empty does not work. Not in place back does work. In place back. What in place does is, let's say we have a vector of pairs of integers. Let's say VC. People, that's what people call it, VC. Let's say now there are two ways to add stuff to this vector. One way is by doing VC dot pushback, and we give in the vector. One, we give in the pair. When we are using pushback, we have to give in the object, the element itself, which is going to be added to the vector. Or one more method is emplace back, in which we do not give in the object itself, the element which we are going to add into the vector. We give in the arguments that we would give to the constructor of that element, and in this case the element is a pair. And when we create a pair, when we do like make pair, we give in to the constructor the two elements that are inside the pair, which in this case are integers. So we give those same arguments here and this thing. So instead of here, when we are calling pushback, we have to create the object and we have to give the object to pushback. But with emplace back, we have to give in the arguments that we would give to create the object, and using emplace back, the object is created at place. So the benefit here is this object will be copied and or like moved. I don't know specifically what will happen, but yeah, the object will be copied or moved in this case. But here the object will be made at place, at the like at the specific place where it is going to be finally stored. So there is no moving and copying anything here, but in this case there is. And another question is why we can call this emplace back without arguments, because that just calls the default constructor, which is empty array. Actually, this is good. I didn't know I can iterate DFS by yes, that is like actually good. I didn't know too. Wait, and you might also want this gist. See, eliminating global state. Okay, iterative DFS is cool. Reversed, instead of making reverse a function, we have reverse as like the code is right there. And place back, instead of this, constructs the vector in place, avoiding a move. Okay, so we do a move. Cool. And const references for adjacency lists that aren't modified, communicates intent and allows compiler optimization. Const references, when we are using references, I guess const references. Okay, cool. And const for the things that we are not changing. And removed the separate reverse. Yes, we did saw that. Okay, why is this like uh, zooming there? Removed separate reverse and removed order dot assign. We didn't have order dot. We did have order dot assign because our state was global, but now it is not global. Okay, cool. Yep. In the background, we have this thing. This is from Chainsaw Man, which is cool. Chainsaw Man is cool. Okay. So we saw iterative DFS in this and Kurasaku function. Not Kurasaku. Kusarazu algorithm. Cool. And this has been 1 hour 42 minutes. And I guess that would be it for today. Yes, today's stream is not long. Yeah, I also started late, so yep, that would be it for today. Yep, that would be it for today. And thank you for being here. How does it work though? Like in emplace, we are not giving any arguments. So what is the default behavior? Like, what does it take then, please? Please ignore my small. No, I will not ignore it. I will answer it the best I can. So when you are calling emplace back without any arguments, it is just going to call a default vector. Like if you were to make a wait, or auto does not make sense. Let's say you have a pair of integers and let's call this object, and when you do not given anything, then the default constructor is called. So the same thing is happening here. When you do not given anything here, the default constructor will be called, and the element inside the outer vector in this strongly connected component vectors, that is the internal element, is a vector of integers. So this is similar to having a vector of integers, so call it object, being called without any arguments. That is like a default constructor will be called. This vector will be empty, will not have any elements at the start, and yeah, that is it. And place back, default constructor will be called, and that would be it for today. Yes, this is not a very long stream, 1 hour 44 minutes, but yep, cool. At least I did stream, which is like I think more important. Consistency. Okay, cool. And that would be it for today. And thank you for being here.